Okay, please go ahead.
Please go ahead.
Okay. Let me take a look. I'll get the pointer out. Oops. Okay, so yeah, good morning, good afternoon, good evening, everyone. Right. So my name is Wantong Li. So it's my great pleasure to be invited here for a talk on this Monday Memories webinar. Right. So as Nima mentioned, the title of my talk today is driving AI efficiency through heterogeneously integrated data-centric computing. Right. So as you can see from the name, this talk will focus on the theme of data-centric computing, but then approach it from how to improve the energy efficiency to execute AI workloads, as well as to looking at how to build this computing paradigm through heterogeneous integration. So let me start off by saying the AI applications have been very popular for a lot of communities, a lot of directions, right, in the past decade or so, right? We have seen a very rapid growth, right, for the use of AI in all of these areas, right? Image detection, medical diagnosis, right? Autonomous vehicles. And then, of course, as engineers, right, we want to understand, okay, where the AI and deep learning have been going to, right? So here, this is a somewhat old figure, right, which is plotting the relationship between the number of operations, right, or even the number of parameters for the AI models versus accuracy, right? So this figure is showing that we do need a lot more operations, a lot more parameters in order to achieve higher and better performance, right, for the accuracy for the AI models. And this growth, right, very rapid growth for the need for the performance and then for the AI models, right, is the reason why we are stacking more and more GPUs in order to catch up, right, with this demand. So what is the grand challenge for us, right, as the computer engineers? It's really the fact that what we are working with, right, which is the Moore's law, right, number of transistors, is actually being outpaced by the scaling of AI models, right? So if you are looking at scaling of AI models, right, so growing, almost 32 times every 2 years, whereas Moore's law is really, failing to catch up, right? So if we are following this, trajectory, right, then we are going to hit the, maximum of the world's energy production very soon, right? If we want to, continue this unsustainable growth. This is the reason why we are looking at new ways to improve computational efficiency with newer trajectories, right? This is where alternative and emerging computing paradigms, for example, data-centric computing, can come in. So I'm sure, audience of this talk have been, very familiar with this type of, analysis, right? So we have a wide spectrum of computing platforms, right? All the way from CPUs, where it's the most flexible, to digital ASICs, which is the most efficient. But then, all of these are still categorized, right, as what's called the, processor-centric computing, right? Because they have been bottlenecked by what's called the memory wall, right? So there are processor-centric platforms. So a quick example of the processor-centric systems, right? Whereas you can see, from this, CPU, right, the cores, and the cache as well as the IOs, right? All of them are being dedicated to the movement as well as the storage of the data, right? Even though we have to move everything to the processors, right? To the local cores for the processing, right? So this is why, right, we are observing the fact that even though we are dedicating so much memory and then the silicon, right, for the data, the system energy and latency are still bottlenecked by data. Right? So again, this figure is also very popular. Right? So if we are comparing, the cost, right? This is the energy cost to do the additions or even the multiply, right? This is much lower than moving something, right, from the SRAM cache. And then if you want to go to the main memory, right, DRAM, then this is even thousands of times more expensive. And then, of course, the latency, right, follows a similar trajectory. So this is why, right, the community is calling for a paradigm shift of computing, right, where we want to move away from the fact that we have this decoupled processor and memory, right? So, again, memory-centric computing, data-centric computing is something that you're familiar with, but here I want to summarize, right, the lessons, or let's say the design philosophies into 3 points, right? And the 3 points here are really the fact that with data-centric computing, right, we want to enable computations closer to or even inside memories, right? This is what we call the near memory or in-memory computing. And then we want to shorten the distance of the data movement, right, whenever possible. Finally, we also want to try to reduce the dimensionality of data, right, that is being transmitted, right? So these are the 3 themes I want to talk about today. So this is also how I outlined the talk, right? So where we want to address each of the themes. And the first one that I'll talk about is to look at how to apply, right, memory, in-memory computations, right, with the data-centric or the memory-centric computing. Secondly, I want to look at how we can shorten the, movement of data with heterogeneous integration. Right? For example, using more than more, right? So more than CMOS, more than what the Moore's law is providing us. Finally, right, I want to look at how we can leverage algorithm hardware co-design, right, to try to reduce volume data, right? So this one, theme 3 is more about some case studies, right, where we look at application level case studies, right, to look at how do we apply memory-centric computing. Yeah. Okay, so let me start off with the first theme, right? So this is the in-memory computing. So in-memory computing, again, it should be familiar to you, right? How we are doing this, at least from a nominal case, right? So here we are trying to, for example, use the CIM, right, as the MAC accelerator, right? Multiply, accumulate. And typically, how people do this is that if you have some sort of resistive memory arrays, right? For example, resistive RAM or magnetic RAM, then we can use the weights, right? Let's say the model, the memory states, right, to denote the memory weights, right? And then the inputs or the activations will be applied on the word lines, right, to select these rows, right, of memories. And then finally, if multiple of these rows are selected, right, then the bit line current, right, can be viewed as a summation, right, of all of the individual contribution of the cells, right? So this is an example of the resistive RAM based or resistive based current summation CIM array. Right? So just to again illustrate, right, the fact we are separating the multiply accumulate into 2 steps, right? The multiply part is really the bitwise AND operation, right, between the input as well as the memory state, right, which can be represented with the conductance, right? So only if the input as well as the conductance, right, which is what the memory is storing, are both ones, will the output be a logical one, right? And then finally, we do the accumulate through the very simple Kirchhoff's current summation law, right, where we add up all of the activated memory cells. Okay, so in this talk, I will be mainly focusing on the resistive RAM-based CIM, right, for AI. Right? So even though some of the techniques that I'll talk about can be generally applied to other memory types as well. So why we want to use resistive RAM, right? So resistive RAM is one of the non-volatile memories, and in the past few years, the community has believed that RAM has emerged from this emerging state, right, to becoming more widely adopted, right, in different areas. So compared to other memory types, it's possible to have very high capacities, right, with multiple level cells, and then be a non-volatile memory, right? It typically has a very low leakage, right, for the standby mode. So this is a very attractive candidate, right, to performing the low cost and low power AI inference, right, for example, the edge devices or the embedded space. So the way that we want to denote, right, resistive RAM into different memory values, right, is really to use the resistive distribution, right? So here I'm showing a binary version of the cell where you have the low resistive state, right, LRS, where we can denote it as the numerical 1. And then vice versa for the high resistive state, right, low conductance, we can denote as the numerical 0. Right? This is how we do the accumulation. So in the past, we have done some, RM-based, CIM tape-out, right? So this is one of the earlier work where we integrated all of the peripheral circuits, right, with the RM module, right, RM subarray. And, within the RM and then the reading, right, we have, of course, using the RM to store the weight, right? So here we can do from MSB to RSB, right, to store the wide precisions. And then the inputs are applied, right, at the the word lines, right, where we can simultaneously activate multiple rows of memories. So for this design, the readout is pretty simple, right? By today's standard, we just use a very simple current to voltage converter, and then we have a parallel VSA, right? Voltage sense amplifiers, right? So this will be a 3-bit flash ADC to sense the activated bit cells, right? So we have taped out this, right, with the TSMC's 40 nanometer technology node, right? So this macro at that time has achieved something about 50 or 60 TOPS per watt, but then by today's standard it's not very high anymore, right? So instead of talking about energy efficiency, right, I actually want to share with you some of the design techniques that address other challenges to perform in-memory computations with RM. So before that, right, so this is again a recap of the compute schemes, right? For the input side, we activate multiple input, right, to basically load the input vector, right? And then with the weight matrix, right, we have the reconfigurable weight precisions, right, going all the way from binary to 8-bit, right? And then finally, we have the the analog marks to select the different columns, because for our design, the readout was quite occupying a lot of space, right? So we have to basically time multiplex between the different columns, and then we use a simple resistive divider, right, to get from the current voltage, and then we do the sense amplifier, right, with a 3-bit flash ADC. So besides, of course, trying to improve the energy efficiency, right, and then the compute throughput higher and higher, what are the other design challenges, right? So this is the focus of this portion of the talk, right? So if you are familiar with analog designs, of course you have heard of the process, right, voltage and temperature, right? So to perform analog computations, which is in nature not very exact, right, it can be more severely affected by each of these variations, right? So this is what I'll talk about one by one, right? To talk about what are the circuit design techniques we can try to leverage to combat these variations. So first of all, right, device process variations. So as I showed you, right, the RM can be divided into multiple states, right, lineated by the resistive state. But of course, this figure is more of a ideal case, right? If we consider a lot of the non-idealities, right? For example, the drift, for example, lack of retention, right? Then it's actually possible for the two different states to collapse into each other, right? This way, it's very hard to draw a clear line to separate these states, right? So in order to combat this, right, in order to make sure that all the states are still very distinct and then, not drifting into each other, right, we have devised a very simple on-chip ret-verify circuits, right? So this is one of the earlier examples of the ret-verify circuits integrated, right, monolithically onto the RM macro, right? So the circuit itself is quite simplistic, right? So we have of course, do the initial form and then to do the iterative sense and program, right, to make sure that the cells that's above or below what we are calling as the window, right, can be reapplied back, right, by either doing set or reset, right. And then we are using the similar voltage sense amplifiers, right, to form this window, right. So the higher resistance, lower resistance, right, two resistance values will make up the window, right? So anything that's outside, we'll try to program it back, right? So with this scheme, right, even with 3 states, right? So this is ternary cells, right? We are able to program a lot of the drifted or wide distributions, right, into a more narrow, right, more desirable distributions to do the in-memory accumulation. Right? So this is illustrated with the black curves, right, before the red verify, and then the color curves after red verify. Right? And then with this, we can also achieve very fast programming speed, right, compared to using just the off-chip programming equipment. Okay, so that was the process variation, right? Then what about the temperature? What about the voltage, right? So with voltage, I actually want to bring up a popular technique, right, which is called the VDD scaling, right, supply voltage scaling. So this is a good way to toggle, right, different systems to different modes, right? If you want to have high performance, right, you go to the high VDDs, or if you want to have the low power, right, you go to low VDDs, right? So we want to also achieve this with the CIM designs, right? But then what is the challenge here? The challenge here is that, especially with the type of CIM scheme we are working with, right, which is the resistive-based, the current summation, right? The fact that we lower the VDDs, right, we actually reduce the amount of the ADC sense margins, right? So this can be illustrated with the, for example, comparison, right, between the top and bottom curve. Right? So in this case, this is the real measurement data, right? If we scale VDDs from 1 volt to 0.7 volt, we're actually reducing the overall ADC sense margins by more than half, right? So this is going to result in more errors for the ADCs, right, during the sensing. So in order to combat this, we actually developed a ECC module, right, integrated into the data array, right? So this MAC ECC will be able to correct all of the errors that happens in the analog domain or the mixed signal domain, right? So basically anything that's happening within the array or during the ADC sensing, right? All of those errors can be corrected. But the correction actually happens after the ADC in the digital domain, right? So the special property of this is that the MAC ECC can correct errors based on the arithmetic distance, right? So this is a good property, right, to deal with the accumulative nature, right, of the CIM. For example, if we go to 7 and 8, right, this is timing distance of 4, but then let's look at the arithmetic distance. It's only a difference of 1, right? So we want to be able to correct this based on the arithmetic distance. Right? And then we also develop some very compact decode as well as the correct logic, right, to enable this within the RM array or the RM CIM subarray. So with this, right, we are able to toggle between different modes, right? For example, high performance, low power modes, while achieving ISO accuracy, right? Meaning regardless of what voltage levels we go to, we can achieve very high accuracies, right? So with the measurement data, right, we are able to demonstrate that with the 1 volt, right, we are able to prioritize the high performance, right, higher throughput, whereas at low power, right, we can emphasize more of the energy efficiencies. So the final challenge I want to share with you, right, for the RM CIM design is on the temperature, right? So if you're familiar with the RM device physics, right, the RM resistance can actually change, right, with respect to the varying temperatures. Specifically, the baseline voltage, right? Baseline voltage will actually rise because of the increase in temperature, right? This is due to the increase in the RM resistance, right? So one of the problems that this poses, for the the CIM computing is actually on the reference design, right? Because before we have assumed, okay, VSA can work independently, but then for almost all the sense-amps, right, ADCs, they actually need a reference, right, to compare to, right, what is the correct windows, right, what is the correct threshold. So the problem with this is that if we are using very rigid references for the sense amplifiers, then at different temperatures, right, the ADC references that's tuned for one temperature is actually not going to work at other temperatures, right? So this is, again, some measurement data, right, we took at both the 25 and the 120 degrees Celsius, right? You can see that the red curve, right, which is the VTC, right, have shifted, whereas the rigid references are staying at the same place, right? So with this, it's actually going to cause a lot of the missing codes for the ADCs, which is because of the mismatch between the reference voltage as well as the sensed baseline voltage. So in order to address this, right, we have to design the temperature independent, or let's call the temperature tracking ADC references, right? So the insight here is that we can actually leverage a portion of the RM cells themselves to form the voltage thresholds, right, for the references, right? So here we are using a small array beside the main data array, right, to give the different voltage references, right, to the VSAs. Right? And a good property of this is that you can actually tune the different states, right, such that the reference voltages can be very fine-grained, right, to provide the thresholds you need. And in our design, we only needed about 5% of the cells to act as the reference cells. So with the ADC temperature tracking, right, temperature tracking ADC reference, right, we are able to demonstrate that all of the ADC output codes can be retained to certain degrees. And then, you know, if we run the software accuracies, right, we can demonstrate that the improvement, right, of the CNN accuracy, right, even at 120 degrees Celsius, if you want to use the on-chip temperature independent ADC references. Okay. So this is the part with the RM-CM macros, right, where we designed the macro itself, but then, you know, try to leverage circuit design techniques to combat the process voltage temperature variations, right, that are, you know, very critical problems, right, within the in-memory computing. So with that, then I'll go to the second theme, right, which is the heterogeneous integration. Right? So I want to, you know, start off by introducing what is heterogeneous 3D integration. Right? So 3D integration is really the fact that we are trying to stack multiple, you know, silicons, right, on top of each other. And heterogeneous is the fact that, you know, this is more of the die stacking, right, as opposed to the monolithic. Right? Monolithic will be within the same substrate. You just grow, right, on top of the same substrate. Right? So the advantage here is that, you know, for the memory technologies, right, we can actually achieve very compact form factor. And also another advantage is that we can integrate multiple technologies or process fabrics, right? For example, here, the AMD's HBM, right? We can integrate the logic process as well as the DRAM dies, you know, inside the same stack, right? So the state of the art for the H3D is the memory on memory, right? So this is for the memory storage applications, right? So for this section, I will talk a little bit about both the memory on memory as well as memory on logic, right, for computing and for storage scenarios. So speaking of AMD, right, so recently my group collaborated with AMD's research team, right, to look at how to develop, you know, the future versions of the HBM, right? So this is particularly the HBM4, right? So as you may know, HBM4 is going to come out soon, if not already, right? So this is one of the latest versions of the HBM. But then, you know, it's actually leaving a lot of gaps for different critical applications, right? So for this folded banks HBM work, we are targeting to redesign or rethink the architectures for the HBM4 to optimize for the random access applications, right? But this is where the bandwidth will be irregular, right? So this type of applications can pop up in the high performance computing, right, HPC, or in the sparse linear algebra, right? As well as, you know, some neural networks, right? All will exhibit this kind of properties. So, you know, without going into too much details, right? So the main idea of this folded banks HBM is that we want to redesign how the bank architecture is being structured, right? So in the conventional architectures, all the banks, right? So each bank will be on one separate DRAM die, right? So for example, you have multiple dies, and then if you call any bank, that bank will be on one or the other dies, right? So for these folded banks, you're actually redistributing the the locations of banks across multiple dies vertically, right? So this is what we call the folded banks, right? So from this figure, right, you can see that one bank can be folded, multiple times, right? In this case, 8 times. And then to support this, we actually have to also redesign the sensing, right? So in this case, you have the hierarchical sensing with the local sensems, and then the global sensems in the base logic die. So we have to boost the signal strings multiple times, right, to make sure that we can withstand the signal communications through the vertical vias, right? TSVs, hybrid bonds, right? So with this architecture, right, we have to redesign the layout as well, right? So the main idea or the main motivation here is that we want to shorten the distance between the where the data is stored, right, in the DRAM cells to the final location, right? For us, then this will be the sense amplifier or the, let's say, the buffers, right? So the two timing parameters we are most interested in is the TCCD, right, the column to column delay, as well as the TCL, right? This is CAS latency. Right? So with these two delays being reduced, we can actually improve a lot of the bandwidth problems for the irregular axis. Right? So with this type of architecture as well as the layout design, right, you can see that the distance of the signal, right, going from the memories to the vias are being dramatically shortened. Right? We have to account for the vertical vias as well, right, TSVs, but then still overall the distance as well as the parasitic RCs are being reduced a lot, right? So this is why we are seeing a very good improvement in the random access performance in terms of the latency as well as the timing parameters. Right? So this is a quick introduction on in how to reduce distance of data movement within a conventional memory applications. Right? So next, I will talk about how to do similar follow similar principles for the 3D stacked in-memory computing. Yeah. So for in-memory computing, I want to motivate this work with transformer technology. Right? So the transformer is the backbone for all of the large models these days, right? And one of the critical blocks within the transformer, right, is the multi-head self-attention. Right? So this is the module we want to try to improve and accelerate. Right? So if you are familiar with the multi-head self-attention, right, you will know that, of course, this will also have different matrix multiplies, but then we have two main versions, right? Two main flavors of the matrix multiply, right? One of them is the conventional linear, right, or the fully connected layers where we have the trained model parameters, right? And then the second one, which is more of the special case, right? We have the intermediate matrix multiplications where both of the inputs are generated on the fly, right? This is where you don't know the inputs beforehand, right? So in terms of what memory technologies we want to leverage, right? In this case, we want to try to leverage, for example, the non-volatile memories like RAM to store the linear model parameters, right? But then for the intermediate matrix multiply, right, we want to try to use the volatile memories, right? Because we have to refresh the contents very frequently, right? So this is where the cache, for example, SRAM can come in. So then this is the problem motivation, right? We want to combine these different memory technologies within the same design, right? How do we achieve that? So with the baseline design, right? Baseline accelerator, we have the multiple parallel cores, right? Each of which will address some of the portions of the windows, right? So this is the baseline design. But then the challenge we run into here, right, is the fact we want to integrate both the RAM and SRAM within the same design, right? Then we can run into the the process issues with the fact that typically the non-volatile memories are lagging behind in terms of the process technology nodes compared to the logic nodes, for example, where the SRAM is sitting. Right? So then if you want to use both technologies within the same design, then we are forced, right, to use the older nodes, right, just to accommodate the non-volatile memories. Right? So this is where the H3D, right, the die stacking can actually come in, right? Where I mentioned that we can integrate technologies from multiple process fabrics, right, into the same design. So with that, then we redesigned the previous baseline architecture, right, into this 3D stack, where we allocated multiple layers for the RM, just to improve the capacity, right, to store the linear model parameters. And then with that, we can actually allocate other layers to do the peripherals, right, for the RM, for example, the sensing programming, and then finally one more layer for the SRAM-based in-memory computing, and then the global buffers, right? So with the H3D, right, you can see that we can actually allocate process nodes from different technologies, right, across this stack, right? So with the RM, right, we can remain at an older technology nodes like TSMC's 40 nanometer, but then we can leverage newer technology nodes like the 16 nanometer for better improvement, right, for the area as well as the power, right? So with this type of partitioning, right, we are essentially remodeling the 2D cores as I showed earlier into a 3D core, right, where the memory and then the sensing and the computing is stacked vertically, right? With this type of structure, right, we are able to demonstrate some improvement in the energy efficiencies, right, compared to a design where all the nodes are 40 nanometers, right? So the improvement partly comes from the fact that we have newer technologies for the ADCs and digital, and then in other parts come from the fact that the distance where the data have to travel becomes much shorter, right, if we do the vertical stacking. But of course, right, with the vertical stacking, especially the fact that we are passing analog values, right, so analog MAC values through the vertical tiers, right, we have to look at how the signaling, right, is doing. Right? So whether the vertical vias is going to affect the signal integrity. Right? So in this case, right, in this setup, right, we have the RM arrays on the top tiers, and then we are doing the in-memory multiply accumulate within the RM tiers, and then we are sending the analog values that's encoding the MAC results, right, down the vertical vias to the base ADCs, right, for the sensing. So with this, then we have to model the RC's parasitic delays, right, for the TSV's hybrid bonds. So overall, right, we are seeing that the parasitic resistance and capacitance actually affect different properties, right? The resistance will tend to eat into the resistive states, right? The values of the RM cells. But then in our case, we didn't find that affected too much because the parasitic resistance is much lower, right, in the magnitude compared to the actual RM values. But then the parasitic capacitance will actually affect the speed of the ADC sensing, right? This is where the some challenges remains, right? Because the parasitic capacitance of the TSVs, especially, is actually in the same order of magnitude as the baseline capacitance. Right? So with the added TSVs, then we are actually experiencing a lower operating frequencies, right? Because the signals will take longer to settle, right? So this is the trade-offs, one of the trade-offs with the 3D stacking, right? And of course, right, another one is the thermal evaluations, right? We also have to extensively model how the the heat is being dissipated, right, with this type of aggressive die stacking, right? So with our evaluations, we are seeing, okay, there's more heat, that's being gathered around the middle, right? This is typically expected for most of the evenly distributed workloads, right? And then within the 3D stack, right, with the 5 tiers, we are actually experiencing an average 15%, 15 degrees Celsius increase compared to a baseline 2D design, right? So in this case, 50, 60 degrees Celsius is still not too bad. But then if we start to stack more and more chips, right, it's going to easily exceed the tolerated levels. For example, HBM these days is experiencing a lot of the thermal issues, right? So this is again another limitations for the 3D stacking that we have to try to address, right, across the stack, right, to make sure that the heat doesn't become too severe. Right? So this is the conclusion of the second part of the talk, right, where we shared with you some of the design techniques to rethink how the both the conventional memory as well as the in-memory computing engines, right, can be re-architected, right, into a 3D stack to improve the performance and then the energy efficiency. So finally, right, I want to share with you several case studies, right, which is surrounding the theme of the algorithm hardware co-design, where we want to reduce the volume of the data movement. Okay, so with this, then I want to motivate with one of the applications for the autonomous driving. Right? So autonomous driving these days use a lot of the image sensors, right, the cameras, to basically capture the scenes and then do the heavy duty the classifications and then the detections backstream, right, downstream. So our motivation here is that these cameras is actually capturing a lot of the data, and some of which are actually redundant to each other, right, in the temporal sense. So we are proposing to place a small filter near the image sensor, right? This is what we call the temporal frame filtering, near the sensor to examine the consecutive frames that's coming in and then drop the ones that we believe is redundant to the previous one, right? So this is where we can reduce a lot of the frames that's been transmitted to the backend processors, so that we can alleviate the bandwidth as well as improve the communication energy efficiency, right? So the way we propose that is to use a very compact CNN, right, near the sensors to examine the consecutive frames. So on the algorithm side, right, so this is a theme of algorithm hardware co-design, right? So then the algorithm side, we want to make sure that the CNN that we propose is very compact, right? So in this case, it's only a 3-layer CNN with a max pool, right? Where then we can determine whether this frame is redundant or not, right? And then we evaluated this with the standard BDD 100K data set, right, to perform the QD track operation. So then what is the hardware side, right? So hardware side is more what we are familiar with, right, with the CM, right? So then this is a slightly different flavor of the CM, right, where we are using the digital CM, right? So for digital CM, the idea is that we have the either tree very close to the memory bit cells, right? So this is, you can think of it as a sandwich, right, between the memory cells, right? We have the memory and then the adder tree, memory, adder tree. Right? So this is kind of sandwiched structure. Right? This is what we call the digital CM. So we are using the embedded DRAM, right, the EDRAM based in-memory computing engines, right, to perform the in-memory computations, right, the accelerations for the CNN that we proposed, right. So without going to too much details on the performance, right? So we know that CRM can improve the energy efficiencies, right? But then I also want to bring in the previous theme, right, in terms of the heterogeneous integration, right? How to possibly die stack the image sensors with other modules, right? For example, the near sensor in-memory computing engines, right? So in this case, the one possibility, right, to integrate CMOS image sensors as well as the compute units and the global buffers, right, is to do the 2.5D stacking, right? So even with the 2.5D stacking, right, so this horizontal distance, right, is still being bottlenecked by somewhat longer distance as well as the communication energy, right? So this is where I want to use this as a case study, right, to say that we can do a similar die stacking, right, for the CIS, right, the CMOS image sensors, right, where we have the top tier with the pixels, right, which will be exposed to the light, and then we can also have other tiers to perform the ADC sensing as well as the near pixel computing, right. So in this layer here, we can do, for example, the EDRAM-based in-memory computing, right, to accelerate the frame filtering algorithm, right? So then with this architecture, right, we can maximize the fill factors, right, for the pixels, because the ADC's peripheral circuits are being allocated to the lower tiers, right? And then we can also follow a lot of the themes from before, right? We are enabling the computations close to where the data is generated, right, which is the pixels. And then we are also shortening the distance between the data movement, right, from the pixels to ADC and from ADC to the near pixel EDRAM-based computing, right? So by the time that the data leaves the this stack, all of the data have been processed, right, in terms of the redundancy checking feature, right, that we proposed earlier. So with the 3D stacking, we are also redesigned some of the circuits, right, where we drive and then sense the pixel values, right, as well as the fact that we can start to integrate other emerging memories, right? For example, some emerging logic or transistors, right? For example, the backend of the line IW transistors, right, where we can use to act as the buffer memories, right, to store the frame data, right? So then with all of the setups I talked about, right, with the 3D stacking, then we demonstrated that with the 3D stacking we can actually achieve very significant power reductions, right, compared to a planar 2.5D integration, right, by just performing the die stacking and then the near sensor computing. Right? So this is one case study, right, where we are focusing on the autonomous driving. So I want to end with another case study, right, which is also one of the recent works. So this is actually for the security, right, for the security of the AI backdoors, right. So here I want to introduce quickly about what is the problem, right. So for the AI backdoors, this is where the adversary can try to poison the data set, right? For example, to add some small triggers to some of the training images, right, training data, and then during the training phase, right, because the the data set is already poisoned, right? So it's actually possible to misguide the training process such that if you show the input data with these embedded triggers, right, then it's possible for the model to misclassify, right? For example, if we are showing the the model the benign samples, right, then the stop sign will be classified as stop sign, right? But then with the poisoned samples, right, the stop sign with the small trigger will actually be misclassified as a speed sign, right? So this is potentially very dangerous problem, right? So and then of course once the poison model is being deployed, right, then whenever you show input with the embedded triggers, right, then this will misclassify, right? So this is what we call the AI backdoor models, right? So without going to too much background here, right? So there are some defenses that's been proposed to protect against the backdoors. So one of them is what's called the transformation-based backdoor defense, right? So the idea here is that whenever we receive the input data during inference, you want to stochastically transform the image a little bit, right? For example, using the affine transformations, right? For example, scale it or rotate it a little bit, such that we can disrupt the positioning or the shape of the backdoor triggers without affecting too much on the clean accuracies of the model, right? So then, where does this kind of transformation-based backdoor defense come into picture, right? So this is where we try to integrate this feature near the sensors, right? For example, again, for autonomous driving applications, right? So here I want to introduce the concept of the on-sensor processing, right? So the near sensor, in-sensor processing. Right? So this is of course following again the similar principles as before, right? We are embedding some of the computational features near where the data is being generated or stored, right? But then besides improving the energy efficiency, latency, right? there may be other benefits, right, to put these processing capabilities near the data source, right? For example, the pixel arrays, right? So here we introduced the Rendai architecture, right, to support this type of uncensored stochastic image transformations to enable a AI-resistant computing platforms, right? And we are enabling this, with some simple, redesign of the peripheral circuits on the sensor itself, right? So the idea here is that we have the, the transformation logic, right, near the sensors, so that we can, whenever the pixel array, captures the data, right, we can stochastically transform the captured image a little bit, right, such that the transformed image that's sent to the downstream processors is already in this, somewhat secure state, right, so that it's much harder for the attackers, right, to activate the trigger or to tamper with the images further, right? So with this, right, then we are able to demonstrate that across, for example, right here we are evaluating the rotations, right, rotations to different angles. So with the rotations, we are able to demonstrate that the clean accuracy, the ACC, can be maintained to certain degrees, whereas the ASR, right, which is lower the better for defenders, right, can be suppressed to below 5%, right, if we perform enough transformations. And then this technique here can also be integrated with the model fine-tuning to further restore the clean accuracies, right, while further suppressing the attacker's attack success ratio, ASR, right? So this is another case study, right, to demonstrate that by integrating some lightweight processing capabilities near the sensors, right, we are able to achieve a very standalone secure sensor, right, for the downstream task. Okay, so then let me summarize my talk today, right? So we went through 3 themes today, right, which are the 3 design philosophies that I summarized, right, at the beginning of the talk. We wanted to enable the computations near or directly in the memories, right? So this is where I demonstrated the RM-based CIM chip, right, with the PVT robust circuit design techniques to address some of the challenges. Right? And then we demonstrated that with the 3D stacking, right, especially heterogeneous 3D stacking, right, we are able to redesign the architectures for both the conventional memory applications, right, with HBM, as well as the emerging, in-memory computing, right, where we allocated different technologies, SRAM, RM, to the different tiers to maximize the area as well as the energy efficiencies. And then finally, we are able to demonstrate the fact that we can co-design the AI algorithms as well as the hardware we use, right, to try to reduce data movement or even to introduce more interesting ideas, right, like the security features, right? So all 3, ideas in order to, enable data-centric computing are really important, right? And I would encourage, all the audience here to also, try to think about the challenges here and then, propose other interesting and then, techniques, right, to further enable data-centric computing, right? So with that, then let me end the talk and then thank you. So I'll welcome any questions from the audience.
Right. Thank you very much, Wantong. Let me stop the recording, and I think we have the first question already.